In collaborative international effort, laser physicists at LMU have built the first hybrid plasma accelerator. Particle accelerators have made crucial contributions to some of the most spectacular scientific discoveries of modern times, and greatly augmented our knowledge of the structure of matter. Now a team of laser physicists led by Professor Stefan Karsch at the Ludwig-Maximilian University, LMU, in Munich and the Max Planck Institute for Quantum Optics, in cooperation with scientists based at the Helmholtz Centre in Dresden-Rossendorf, HZDR, the Laboratoire d'Optique Appliquée in Paris, LOA. They have built the first compact two-stage plasma-based accelerator in which particles in a plasma wave initiated by a powerful laser are used to accelerate a beam of electrons. Particle accelerators have become an indispensable tool for studies of the structure of matter at subatomic scales, and have important applications in biology and medicine. Most of these systems make use of powerful radio frequency waves to bring particles up to the desired energy. One drawback of this approach, which has been the standard methodology in the field for decades, lies in the risk of electrical breakdown when very high levels of electrical power at radio frequencies are coupled into the accelerator. This potential risk effectively limits the field strengths attainable, and is one of the reasons why these accelerator systems are typically many kilometers long. Physicists have therefore been exploring ways of reducing their size by exploiting the fact that a plasma can sustain much higher acceleration fields. In this case, the electric field generated by a powerful laser or a particle beam is used to strip electrons from the atoms in a gas and to create a wake similar to the one produced by a speedboat on water. Electrons surfing on that wake can get accelerated to nearly the speed of light within a d. Studies on plasma-based acceleration with the aid of lasers, i.e. laser Wakefield acceleration, LWFA, are now in progress in many research institutions around the world. In contrast, work with accelerators based on particle beams, a field which is known as Plasma Wakefield Acceleration, PWFA, has so far been possible only in large-scale accelerator facilities, e.g. CERN, DESY and SLAC, although it offers a number of advantages over LWFA. For example, particle beams do not heat the plasma as much as laser beams and allow to use a longer accelerating distance. This in turn promises to improve the quality of the beam and increase its energy, parameters that are very important in terms of the technique's potential range of applications. In their experiments, the authors of the new study were able, for the first time, to build and successfully test a practical and compact particle-based plasma accelerator. The essential breakthrough lies in the fact that the PWFA, which accelerates the final electron beam, is driven by a particle beam from an LWFA. The latter is itself highly compact, so that the hybrid plasma accelerator is only a few centimeters long. Moreover, simulations indicate that the acceleration fields are more than 3 orders of magnitude higher than that attainable in conventional accelerators. Another promising result of the study is that the data obtained at LMU are confirmed by complementary tests performed with the DRACO laser at the HZDR. Dr. Andreas Döpp, a member of the Munich group led by Professor Stefan Karsch, points out that, only a few years ago, the practical realization of such a combination would have been unthinkable. The hybrid accelerator was made possible by subsequent developments in the design of laser-based accelerators, which have led to tremendous improvements in the stability of the beam and in other vital parameters. Much of this progress has been made at LMU, following the installation in the center. The successful demonstration of the hybrid plasma accelerator represents the latest advance ahead. We had already shown that our compact plasma accelerator behaves very similarly to its conventional and far larger conventional cousins. So we are confident that we will be able to generate extremely bright electron beams with this setup in the near future, says Stefan Karsch. Before the technology can be applied on a wider scale, a number of outstanding challenges must be overcome. But the team are already considering a variety of possible contexts in which such instruments would be highly advantageous. For instance, research groups that have not had easy access to a particle accelerator could utilize the technique and develop it further. Secondly, our hybrid accelerator could serve as the basis for what is called a free electron laser, FEL, says Dr. Ari Erman, who coordinated the experiments at the HZDR. FELs are highly prized radiation sources, which can be used for extremely precise characterizations of nanomaterials, biomolecules and geological samples. Competition for access to these sources, such as the European XFEL in Hamburg, has been correspondingly intense. If such large-scale X-ray lasers could be complemented by the new plasma-based technology in future, such more compact sources could potentially be made available for a broader user base, therefore boosting research with brilliant X-rays as a whole. Thanks for watching. Please subscribe my channel for more updates.